Okay, we want to find how many mole of dye is in this solution. So you take a small part of it and put it through a HPLC. So it'd be running through the column, and you'd have a recorder after the HPLC. The recorder would be measuring a time. So you're waiting, nothing's happening, and then all of a sudden a peak would appear, which is the dye coming out. So the time that it comes out is specific for that HPLC, for the stationary phase, the mobile phase, the temperature, etc., for the dye. The area that it takes up, the peak area, means how much is in there, in particular, what concentration it is. So at the moment we can see it's this concentration, but what does that mean? We don't really know. So what you would have to have done before this is put known concentrations of our dye solution through and look at the peak areas. So if it was 1 milligram per litre, maybe you get a little bit like this, and then you do it again and you get another peak that's 2 and another peak that's 3. So you can see that your peak's kind of between the 2 and the 3. So you do it over and over and over and look at the peak areas of the known standards. And then you have to plot, rather than just doing it by eye, plot a graph of those peak areas against the concentrations. So in other words, a calibration curve. So a calibration curve is your standards that you've put through, that you know the concentrations of, and you've measured the peak areas, and then you draw a line of best fit. So then you put your solution through with its particular peak and use your calibration graph to work out concentration of your particular solution. So you read the peak area, go across to the graph and down. Use rulers for this, make sure that it's exactly the right amount. So the question was, what's the number of moles? So you've got the concentration of your solution. So concentration is the number of moles in a volume. You know the volume, so you would need to rearrange that equation to find the number of moles. Okay. Yeah. All right, so what happens though if you do your unknown and it's really concentrated, and when you get the peak area, it goes way off the graph? Can you make your line longer? Can you extrapolate it, that means, and then measure way back up here? No, you can't. If you extrapolate it, the reason that's called a calibration curve is that it's linear for a while and then it may curve. So as the concentration gets higher, the peak area may not reflect the concentration. So you can't rely on your graph being straight. So what do we do if our solution is too concentrated and goes off the graph? We have to dilute it to bring it within the range of the standards that we've used, within this range, not even really down here or above, but between the standards that you've used. Okay, so diluting it, this is kind of showing our little volume with our dye in it, and then if I add water to it, that's what diluting it means. So I've added water and you can see it's less concentrated. So if I show, I've got like 10 dots representing our dye here and 10 dots, and I've spaced them out so it's less concentrated. So it's the same number of moles but in a different volume. So the dilution equation is based on that idea that it's the same number of moles. So the number of dye particles in each is the same because you've just added water to it. So our initial number of moles in the concentrated is the same as the final number of moles. So because N also equals C times V, which we did before, I can substitute N for C times V, concentration and volume, because that's what we read off our calibration curve, the concentration. And we want to know, so we're reading off the concentration in our diluted one, and we want to know the concentration in the original one. So we've got the two volumes. The reason that it's multiplied like this is that if we just put some numbers in to show that 3 times 4 equals 12, and 2 times 6 also equals 12. All right, so the reason that I'm showing you this is if two particular things that you're measuring, if when one goes up and the other one goes down, if they alternate in how they behave, then you can multiply the numbers and end up with the same number. So if this is the volume that we had at the beginning, when we've added water, if the volume goes up, the concentration will go down and they will still equal each other. All right, so that's why we have these two equations. This volume has gone up, that concentration has gone down, and those two things will still equal the concentration and the volume that we had originally. All right, so we've done our example with dye, but really we want to do examples that are with things in life. So this could be alcohol. Our dye particles could be alcohol in wine maybe, or alcohol in your blood, ethanol. So if we had diluted it and done the same thing, we're measuring the concentration of this, and then we're going to work backwards to work out the concentration in our original one. So you put it on your chromatogram, get your peak area, find your peak on your ethanol calibration curve. This one, you notice our units have changed with all of these. The only thing that's always the same, the only thing that's different is the units that you use. So this one is, I'm using percentages, which is how many grams or milligrams in mils or litres. So we've measured it across, measured it down, and we've got our concentration in the diluted one. Okay, so our original volume, let's pretend it's 20 mils here, and the volume that we've diluted it to, let's pretend it's 100 mils. And if we read our concentration on the graph, we can see it's kind of about 2.3%. It's mass in a volume, so percentage is always out of 100. If it's percentage and it's a mass, it's always grams in 100 mils. All right, so a 2.3% solution is 2.3 grams in 100 mils in our diluted one. So we want to know how much is that in our concentrated one. So if we want to know the original concentrated one, we take V over and divide it on this side. So we're looking at the concentration in our 20 mils, and we're multiplying it by the volume that our diluted one, and the volume in our original one. Even if that's concentration is grams per litre, we don't really need to convert these to litres because these units will cancel out. So it kind of just makes it a bit easier for this particular equation, not for C equals N on V or M on V. Okay, so we've got 2.3 grams per 100 mils. 100 on 20, some of you probably realize, is 5 times. So our concentrated one is actually 5 times more concentrated than 2.3 grams in 100 mils. It's 11.5 grams in 100 mils. Or another way of saying it is that you've got an 11.5% solution of alcohol. And lots of bottles of wine are around about 11.5%. Pause it.